So many elements don't follow the octet rule to a T. Some of them have electron deficits, and some of them have expanded octets, and we're going to cover a bit of that right now. So some of those that have electron deficits are totally cool when they have fewer than 8 electrons in their valence levels. And so beryllium, for example, is cool with 2 pairs of electrons, which is 4 electrons total. And boron is considered full when it has 3 pairs of electrons, which is 6. And so that's not that full 8 that we're used to, but it still is okay because they are electron deficit. And some of them have expanded octets, and so they can have more than 8 electrons in their outermost energy levels. And this is specifically nonmetals from period 3 and beyond, specifically in phosphorus. So not those first two, not silicon, but starting with phosphorus, the nonmetals can expand their octets. And this is because those d orbitals, there's a lot of tough chemistry going on between how the electrons are able to bond to those, but really what matters right now is that it's nonmetals beyond phosphorus are able to expand the octet. So, for example, with BeF2, we have beryllium and then 2 of fluorine. And using our little trick, beryllium is in group 2, meaning it has 2 valence electrons, and fluorine is in group 17, having 7 valence electrons, and then 14 plus 2 is 16 valence electrons to work with. So we set it up like any other Lewis structure, with the element listed first in the center, beryllium, and fluorine surrounding. And so we start to count it out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So our fluorines are good. But usually we would be like, hey, beryllium doesn't have a full octet, but that's okay. It has those 2 sets of electrons right there, 2 pairs. And as we saw before, beryllium is full with that. And so that is good. So the bond here is beryllium to fluorine, and the electronegativity of fluorine is 4.0, and that of beryllium is 1.5, and that difference is 2.5, which is very much so on the polar part of the spectrum. So it is a polar covalent bond, which means we add our dipole arrows and partial charges. Since fluorine is the more electronegative, it gets that delta negative on both ends, with beryllium getting that little delta positive and the arrows pointing to fluorine, with the plus signs near beryllium. So with PCl5, we have phosphorus and then chlorine 5 times. So again, with those tricks, phosphorus is in group 15, therefore it has 5 valence electrons, and chlorine has 7, with it being in group 17. And the grand total here is 40 valence electrons. And so we also start with phosphorus in the middle because it's listed first. Phosphorus, and then surround it with chlorine. The spacing doesn't have to be perfect, but it should just be clear that it's evenly split. And so we start counting this out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. So we're all out of valence electrons. The octet rule has been satisfied with chlorine, and phosphorus is the one where that expanded octet rule begins. It starts there. Third period, life is good. And it's okay that it has 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, because it can have that expanded octet. So we don't have to try and mess around with all those other double bonds and all that. So our only bond here is phosphorus to chlorine. The electronegativity of chlorine is 3.0. Phosphorus is 2.1. The difference there is 0.9, which is a polar bond, meaning that when we do our dipole arrows and partial charges, chlorine is more electronegative, and so it has, so it gets the delta negative, with phosphorus getting that delta positive, and all the arrows point out to chlorine with their little pluses on the end closest to phosphorus. Final example, XeF6, we have xenon, and then fluorine over 6 times. As a noble gas, xenon has 8 valence electrons, and in the 17th group, fluorine has 7. And this comes to a grand total of 50 valence electrons. And so when we start doing the Lewis structure, xenon is in the center, with the fluorines surrounding. And we just start going to it as usual. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. Now all our fluorines are good, but we still have 2 valence electrons to go. But since xenon has that expanded octet, we can just throw those last 2 on it. So all 50 of our valence electrons are there, everything is satisfied, xenon has that expanded octet, and that's good. The bond here is xenon to fluorine. The electronegativity of fluorine is 4.0. Xenon is 2.6. The difference is 1.4, which is polar. So we have a polar covalent bond. And so our dipole arrows and partial charges. Fluorine is more electronegative, so it gets that delta negative. Xenon getting that delta positive. And all those arrows point out to fluorine with their little positive ends toward xenon.